Well, welcome back, everyone that's going to be watching this recording later. For today's class, we're going to be going through section 8.1, moving into 8.2, and the longer section we'll probably come back to on Thursday will be in section 8.3. Cool thing about section 8.3 is we're going to be revisiting some of the exponent laws that we saw before. So this will be a good chance for us to relearn some of those, practice them a little bit further. Our upcoming quiz number 8, this one's based off section 7.5, will be due on Thursday. So let's jump back into the notes. Last time we left off right around here. We got through example 1, started example 2. Our idea was we were defining what we mean by a square root, a cube root, a fourth root, fifth root, and so on. We said the square root of the 81 is 9, because we checked if we square 9, we get 81. When it was a negative root, negative 81, this one was not a real number because there's no possible way to throw in a value inside the check, raise it to power 2, and get something negative. However, if it was a negative inside a cube root or any odd numbered root, this one did have an answer. Take negative 7 to power 3, and it becomes a radicand, negative 343. So the major issue was this was a square root, the index was even, with a negative on the inside. This one was defined because we had the negative on the outside. It's just shorthand for negative 1 times the fourth root. 2 to the power 4 came out as 16. So this whole fourth root turned into a 2. And likewise, just for extra practice, we did a fifth root. 2 to the power 5 turns into the radicand of 32. And so we said the fifth root of 32 was 2 itself. What the next section is going to be all about is when the numbers on the inside don't simplify in this kind of nice and clean way, when the answers aren't integers and they turn out to be irrational numbers. Before getting to that section, we also looked into this formula. If there's a variable in the problem, then we can simplify with two different ideas. We're always concerned whenever the index is even. The nth root of a to the power of n is not just a like it would be if the index was odd. If the index is even, so the square root, fourth root, and so on, you have to throw in the absolute value. So these problems go pretty quick. The fifth root of x power 5 is just x. The sixth root of x to the power of 6, well, because the index is an even 6, came out as the absolute value of 6. So practicing just a couple more further before we go into the next section, another big observation that we made was the index of the root is just dividing the exponent. So here we have another even index, an index of 4. The result is just going to be x to the power of 12 fourths. But because that index is even, we also have to throw absolute values on this. So this turns into absolute value of x cubed. Do it again here on this version. We have an odd index, so we don't need to worry about the absolute values. We'll just get x to the power of 24, divide by the index of 3, and this turns into x to the power of 8. So these questions go pretty fast, in fact, once we get to some pretty good practice. Something like this looks like it's a little bit more involved, but if it's a sixth root involving 64, we can check with a quick calculator. We saw that 2 to the power 5 is 32. We raise it to power 6, we just get a 64. So we can break this down by first writing out that this is the sixth root, an even index, so we'll have to be careful with absolute value. 64 can just be rewritten as 2 to the power of 6, p power 12, q power 18, just go in as before, and then the index divides all of these exponents. Hello, folks, making it in. So on our next problem right here, we're going to take 2 to the power of 6, divide by the index of 6, p power 12, divide by the index of 6 again, and then q power of 18, divide by 6. Because we are taking the even index, the sixth root, we have to put absolute value around this whole thing, and then simplify from there. So the big takeaway is whatever the index is for the root, it will divide into the exponents. So on the next line, this turns into the absolute value of 2 to the power of 1, but 2 to the power of 1 is just itself. Here we'll get p squared. And here it'll come out as q to the power of 3. We can simplify even a little bit further. Since 2 is always positive, p squared is always positive, q to the power of 3 is the only thing that could potentially be negative. This could be rewritten as 2p squared times the absolute value of q power 3. So these were the last two problems that we left off before we went to the weekend last week. The next section is going to be pretty short, kind of like this one. But any questions at the moment, folks, finalizing these last two?
Why are there fractions as exponents?
That's the main idea with what's going on with the index. The index itself divides right into whatever the exponent is. And that's a good observation. That's exactly what we're getting into in section 8.3. Let's open it just as a preview. It's called simplifying rational exponents. And that's the major idea. It turns out that the nth root of anything, a, is 1 over a to a power of n. So it's really just a fractional exponent every time you take a square root, a cube root, and a fifth root. And it gets even more interesting. If you write down something like a to the power of m divided by n, so a full-on fraction, really you're just taking the nth root of a to a power of m. You could even write them backwards as a to the power of m divided by n is the nth root of a, and the power of m can go on the inside. So that's the major thing that we're going to be connecting with when it comes to square roots, cube roots, fourth roots, and so on. We can write them as fractions at the same time. That means the exponent laws are back on the table for us. We'll be practicing them some more when we get into section 8.3 fully. Other questions at the moment? Okay, well, we finished off section 8.1. Next, we're jumping into section 8.2. The idea of 8.2 was every problem in section 8.1 simplified in a nice, clean way. But that's not something we can guarantee every time we solve a problem like this. And so 8.2 is going to show us how to simplify some trickier things, like if it's the cube root of x power 7, now the index 3 doesn't divide 7 evenly, or square root of 20, x power 11. Well, it's not like taking the square root of 25, so now we need different kind of strategies to simplify these problems. Before we jump into example 2, we should start with example 1 and the formulas. We have two major formulas that's going to assist us in simplifying the roots. The nth root of a product, a times b, can be broken down in this way. We can just break it down as the nth root of a times the nth root of b. For example, if we had just a quick problem to go along with this formula, it could be something like the square root. Here the n is implied to be 2 if we leave it blank. We can throw in something nice like a 9 times a 25. And order of operations ordinarily says you have to take 9 times 25. But this product rule for square root says you can do it in a different way. You can break this across multiplication, take the square root of 9 times the square root of 25. And that's convenient because this is a far easier process. The square root of 9 is 3. The square root of 25 is a 5. And so this comes out just as a 15. And same idea with this one. If you have a fraction in the problem, you can split up the fraction and think of the numerator and denominator as just two independent problems. So for an analogous example, if it was 9 divided by 25 and we want to take the square root of this, we could just split it up as the square root of 9 divided by the square root of 25. Take the square root of the numerator, which is 3, square root of the denominator, which is 5. That's a simpler process than dealing with the fraction itself. Well, those are the two fundamental formulas that we're going to be using in this section. But before we make use of them, there's some exceptions to this formula which are unfortunate. Algebra works really great if there's multiplications and divisions, But algebra tends to go kind of awry whenever there is additions
Would
or
the first
subtract.
one be the square root of 25?
Yeah, absolutely. So with the plus there, we would take square root 25. We're just following order of operations at that point.
And if I'm correct, I assume the next one down is probably going to be 7?
Yeah, absolutely. So down below, square root of 16 comes out as a 4. Square root of 9 comes out as a 3. So just like you said, it comes out as a 7. So the big observation, though, is notice what happened. They're not the same value whatsoever. The 5 and 7 came out differently. So what it tells us is these formulas, which work really nicely because we're multiplying or dividing, it doesn't work for addition. There's no way to take root a plus b and get a root a plus a root b, because as we see here, as you observe, they come out as different values. So this is the big warning when it comes to square roots, cube roots, and so on. The addition wasn't the thing that was bad. It could have been addition or subtraction. This formula breaks down completely. Other questions about that so far? Okay, so they're great formulas when they work. That's when there's multiplication or division on the inside. But if there's a plus in the middle, these formulas break down. They can give you a different answer if we try to take the square root of 16 and 9 independently. In fact, we've seen this before. For example, there's an exponent law that says ab squared, that's just a squared times b squared. But if you do a plus b squared, you know what? That's totally different. Here you have to FOIL a plus b times a plus b. When you FOIL that all out, you get a squared plus 2ab plus b squared. So the square of a plus b is not just a squared and b squared. There's a middle term when you fully FOIL out this whole thing right here. Same problems with the square root formulas. They work nice only in these two cases. So keeping those in mind, here's how the next problems are going to go. Here's the same two formulas again, just for a quick reference. In the last section, we had to be kind of careful with whether the index was going to be odd or even. If it was an even index, we had to use absolute values. But we're going to make an assumption just to make the algebra a little bit more cleaner. That's pretty common in chapter 8. We're going to assume all variables represent positive real numbers. That means we're not going to have to put absolute values on things like we did on just the very last section. So we want to take the cube root of x power 7. The trouble is we can't do like what we did just before and write the fraction 7/3. We have to simplify this in a slightly different way. But here's the big idea. We can use this product rule right here and split up the square root of a times the square root of b. We just need to say what is the a and the b. I keep saying square root, that's a cube root rather. The index is 3. With this x power 7, we can break it down as an x power 6 times x. That's just the ordinary exponent laws that says this would multiply together to give us x power 7. And now the part that we can actually simplify is this one. The x that's left behind is just going to stay as the cube root of x. This is the part that doesn't simplify. On the next step, we can rewrite using this formula that we have the cube root of x to the power 6 times the cube root of x. So that's how this formula works. We broke it into the part we can simplify nicely. This is like the problem that we saw in just the last section, 8.1. And this is the part that doesn't simplify. So now we have x to the power of 6. We divide it by the index 3, so that's just going to turn into an x squared times the cube root of x. So the answer altogether, after we do this division, is just x squared times cube root of x altogether. So that's how that product property works to help us start to simplify things down. Any questions on the moment, at the moment, getting through part A? Okay, let's try out the next one. A little bit more going on. We have 20 x power 11, but we can still break this down in the same sort of way. The last one had an index of 3, so we were looking for things that were divisible by 3. And the 20 is an extra thing we have to worry about, but 20 can break down by rewriting it as 4 times 5. The 4 is nice because we can take the square root of 4. Square root of 4 is just a 2. 5 is the thing that's just going to stay behind, much like the cube root of x. X stayed behind on this one. We can now break down x power 11, just how we broke down x power 7, and rewrite this whole thing as square root. First, 4 times 5. Then x power 11 can be factored as x to the power of 10 times x. X to the power 10 is great because power 10 is divisible by what the index is here, 2. We could take the square root of 4, and the stuff that's left behind, just like in the last problem, is just going to be the 5 and the x. So if we use this property once again, we can rewrite this as square root 4x power 10 times the square root 5x. So this is the stuff left behind in blue. That's the stuff that's like the section 8.1 problem that we can calculate exactly. And here's how the next step would go. This would just turn into the square root of 4 comes out as a 2. The index, which is 2 here, will divide x power 10. So this becomes x to the power of 10 halves times the square root of 5x. And if you put just an x power 5 right here, that would have been a good idea. That would save you a step. But just for the sake of showing that step on the notes, I'll write it in here as well. The answer is now just 2 x to the power 5 times the square root of 5x. And then that's the whole answer to what is a square root of 20x power 11 simplified. It gets kind of messy, but just kind of organized in the stuff you can take the square root of and the stuff that just gets trapped and left behind, the 5x part. Any questions on these two at the moment? Okay, let's try out another one just to get the good practice in for these. Really, the only way to make this harder is just to throw in more stuff, like say the fractions. Notice we've only really used the first formula when things multiply together. With the fraction, you have things divided, and then we can do a little bit more with that as well. Lots going on with this one. We have 54, 125. 125 is nice because 5 to the power 3, check in the calculator, comes out as a 125. I rose it to the power 3 because we're about to take the cube root. So this part's not too bad. Cube root of 125 is just going to come out as a 5. The x power of 9 is kind of nice as well because 9 is divisible by 3. But the variable y is a bit of a nuisance. Probably the best strategy to deal with this is simplify by dividing y into y power 12, and also work with the 54, see what we can break down on that one. So first step is really just simplifying this down. Let's work on the 54 first. 54, if we factor this down, can be rewritten as 2 times, well, 2 would go in there, let's see, 27 times. But then 27 is already a great number. That's 3 times 3 times 3 makes up 27. So 54 can be rewritten as 2 times 3 to the power of 3. So we'll put that in that position. For the variable y, we're just using the exponent laws. We're using this version right here. A to the power of m divided by a power of n. It's just a subtraction of exponents. So y power 12 divided by y power 5, that's just y power 7 left in the numerator. So a really good idea to simplify these first whenever you can get the simplifications, or else these problems can become much bigger than they ever meant to be. So this turns into cube root For the 54, let's put in 2 times 3 to the power 3. Then we have x power 9, y power 12. Actually, let me take off that highlighting there. Y power 12 divided by the y power 5 gave us just y power 7. Divide by 125. Well, actually, I think that highlighting is okay. We'll take another step on this to organize further. I like the factorization here in yellow. It tells us what part's the perfect cube, 3 power 3, what part stays behind, which is just the 2. But this y power 7 is also a nuisance. We want to factor this one down so that we can get the perfect cube part and then the stuff left behind. So one more step to organize. This is a cube root of 2 times 3 power 3, x power 9, and y power 7. We don't want to write this as y power 5 times y like we did in the other problems, because 5 is not divisible by 3 either. We could write this instead as, say, y power, rather, 6 times y. So if we just take off one factor, like the ones we did before, the 6 right here would be divisible by the 3. The 125 in the denominator, we just checked in the calculator, is 5 to the power 3. So because the index itself is 3, this part here, 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 and here is the good stuff. That's the stuff we can take the perfect cube of. And everything else, this part and this part, is going to stay trapped forever inside the cubed root. So really our first steps with doing this was just organizing and simplifying. And here's the steps where we're about to simplify this down. First, let's go in order. The cube root of 3, that's just going to be 3 to the power 1. The index of 3 divides into that 3. For x power 9, this is going to be, let's write in that step, x power 9 divided by 3. And if you just put in an x cubed right here, that would have been just fine as well to save a step. Likewise, for the variable y, that's y power 6 divided by 3. And left behind in the numerator is the cube root of 2y. The denominator, the index of 3 gets divides into the power 3 here and leaves behind just a 5. So last step we can take just to clean this all up is do those two divisions. The answer to this is 3 x cubed y squared times the cube root of 2y divided by 5. A lot of stuff that was working for us on this one. We used two things at once. We used the rule that we could split this, taking the cube root of the numerator and the denominator. And also there's multiple factors in the numerator, so we use this formula as well to split this up. Any questions at all, folks, on how the process looks? Okay, let's try out another one. Again, just for the sake of practice. Looks like I forgot to put a space there. So now example 3 with a space. This one looks pretty tricky as well. We have 128 U13B power 8. It's also a fifth root, so that's a pretty large index. First, let's deal with this 128. 2 divides it, so let's see if we take 2 to the power 5. Well, that would give us a 32, so that's not super helpful. Let's maybe get a factor tree going with a 128 like we did before. So 128, well, 2 can go into there 64 times. 2 goes into 64 32 times. We know 32 is 2 power 5, but we started a factor tree, so let's take it down to its completion. 2 goes into 32 16 times. 2 goes into 16 8 times, or getting down there. 2 goes into 8 4 times. And 2 goes into 4 2 times. So count them up. There's 1, 2, 3, 4, 5, 6, 7 factors of 2, which means 128 is 2 to the power of 7. But if the index is 5, best way to write that is 2 to the power 5 times 2 squared. Or you could say 2 to the power 5 times 4. So we'll make that substitution 128 for our purposes is best written in this different kind of way, 2 to the power 5 times 4. Well, that starts us off. Sometimes the hardest thing about these is dealing with the actual numerical part. The variable part's not so bad because it's already something raised to a power. That's what we want to get down to see how we could organize the powers of 2. Let's hide that one down there below for a moment. So next step is to rewrite this as fifth root. 128 we can put in as a 2 power 5 times 4. That part there, highlighted in green, we can take the fifth root of. We'll factor u power 13 as well. Maybe best way to factor this one would be u power 10 times u cubed. That's because the index of 5 can divide into the power of 10 evenly. And we put in the largest exponent we can put in that position by the red dot. That's divisible by the index, which is 5. Leaves behind u cubed, so that's the part that's staying inside the fifth root. And same idea with this one. This can be rewritten as, let me take off the highlighter, v power 5 times v cubed. We could take a fifth root of that part. And maybe before doing all of that, I did notice one thing. Should have looked before I leaped. We could just simplify u power of 8 and u power of 18. That would probably be the better choice on this one. Let's actually just do the simplification here and then take another step. If we do v power of 8 dividing into v power of 18, we're using this exponent law. The largest exponent is in the denominator, so we just take 18 minus the 8. So this 8 will subtract from this 18 and leave v power 10 in the denominator. And that's way easier to deal with now that we simplified it, so it seems like this problem is just designed to work in that easier way. The index of 5 will divide into this 10, and into that 5. What's left behind is just the 4 and u cubed. So this is how essentially each one of these problems go. Any questions at the moment before we simplify this down? Okay, again, if you write this down, you can just put in 2. For u power 10, you can put in u squared. But connecting the concept of how this works is this index of 5 divides into the exponents of these numbers and these expressions. So rewriting this, you could say this is 2 power 5, divide by the index of 5, u power 10, divide by the index of 5 as well. Then the numerator is also going to contain the fifth root of 4 u cubed, the part we couldn't simplify down any further. Denominator is going to be v power 10, divide by the index of 5. Now to do the divisions, but that's not too bad. So this turns into altogether 2 u squared, fifth root of 4 u cubed, divide by v squared. In that stage, the part B is over. That's all we have to do for this problem. Any questions at all getting through this one? Okay, this is pretty much this section in a nutshell. What we're going to be doing in the next part is dealing a little bit more with what we were describing, the actual exponent properties themselves. We're seeing that exponents are just kind of a natural part of whenever you're dealing with the square root, cube root, fourth root, or even a fifth root like we saw here, and so on. And so that's what section 8.3 is going to be dealing with. We'll also be studying these exponent laws once again. That's a great opportunity, makes it a semi-review section at the same time. But before doing that, let's do one more slightly nasty looking problem, the part C down here. Worst thing about it is the 16807. Sometimes you might be facing large integers like this one and you have to compute it. We're dealing with the square root, so we want something to an even power if we can find it. What I would do right away if you see large numbers like these is immediately go to the calculator. We can see what is divisible into 16807. 2 certainly doesn't divide, it's odd, but just for the sake of emphasis, this is what we would get, 8,403.5, but we're looking for even divisions. So we'll bump up the denominator to 3. 3 doesn't divide. Because 2 didn't divide, neither would 4. If we tried, that's what we get, a decimal number. 5 won't divide because a number ends in 7. It has to end in a 0 or a 5 for 5 to divide. And if we try, that's what we would get. 6 doesn't divide because 2 and 3 didn't divide. And you get a repeating decimal if you did try to divide by 6. I don't know about 7. That's a hard one for me to think about. But that's what we want. 7 divides into 16807 2,401 times. That at least starts this off. Let's start a big factor tree for this. 16807 we know is divisible by 7, so that's helpful information. It goes in 2,401 times. Now, because the original number wasn't divisible by 2, 3, 4, 5, and 6, neither will this one. So the next number to test is division by 7 or something even higher. 2401 divide by 7. It goes in evenly 343 times. 343, and I think that's 7 times 7 times 7. I don't know for sure, so let's keep on testing this out. 343 divide by 7 goes in evenly 49 times, so we can say divide by 7 again. We get 49, and 49 is a perfect square, 7 times 7. We have altogether 1, 2, 3, 5 factors of 7. So 16807 is just 7 to the power of 5. You know, it doesn't hurt. Just for a sanity check, let's go back to the calculator. Take 7 to the power 5, just as another look at it. 16807, all the digits in the right spot, so we've got the good factorization. The integers are the hard part. Actually, the variable stuff, u power 12, v20, and so on, even if the exponents are large, it's in a factored form, making them much, much easier to handle. That's the nasty part, the actual integer itself. But it factors in this way. Because this is a square root, the index here is 2, whether it's written or not. Let's write it in just for the sake of a visual. It doesn't have to be, it's implied to be a 2. That means we want this to be a power of something even, so 2 can divide into it. So we'll factor this as 7 to power 4 times 7. So that's how we'd be writing this one down. This is the perfect square part we can square root. That's the part that's going to be left behind. So the first step is just factoring things that need factoring, usually the integers. Next step is just an organizational step where we factor a little bit more. Let's make that kind of long to fit everything in. 16807 is 7 power 4 times 7. We're keeping the same color coding. The things in blue are the things that are going to stay behind. The things that are in green are the perfect squares in this problem, the stuff we can actually calculate the square root of. U power 12 is a good one. The power here is even. Same with V power 20. We don't have to do anything to that one. But W power 65 is a nuisance. But our whole strategy is just peel off one exponent of W. It'll turn into W to the power of 64 times W. Don't forget, it has to go back to power 65, so equality is maintained. So we just put in one extra W here. Exponent laws, let those combine back to W power 65. X power 80 is just fine the way it is. And now we can take the square root right at this step. What's left behind is just the 7 and the W. And everything left here in green, we just divide their exponents by 2. So let's take a shortcut here. Let me know how this feels as a shortcut. I would write this one in as 7 squared. I'll need another step to call that 49. This would be u power 6, because we're dividing that exponent by 2, v power 10, w to the power 32, skip across that w factor, go to x to the power 80, and this will be x to the power of 40. All the exponents just got divided by 2. Then what's left behind is just the square root of 7 and w. Last step is just to rewrite 49 here, so nothing major. It's 49 u power 6 v power 10 w power 32 x to the power 40 times the square root of 7w. At this stage, the problem is over. This is about as nasty as it can get in this section. The only thing that made it really nasty was the large integer. Another tricky problem is if there's fractions, you have to split across numerator and denominator and potentially simplify first, like in this one. But this gives us a good idea of what simplifying root expressions is going to look like. The next section, we're going to return more to this concept of what is going on with the fractional exponents, the next ideas. Well, any questions at the moment, folks, getting through this section? Yeah, absolutely. For another one with the fraction, let's try out something that goes like this. We have to come up with a root. So let's go for, how about, we did a fifth root on this one, a cube root on this one. So I think the most variety would be good for us if we did a square root this time. So now for the square root, let's do something kind of strange, like maybe 162 over 2, maybe x power 39 over x cubed, y power 13 over y power 24. Yeah, absolutely. Thanks for suggesting it. So this will be another great one for variety. These ones aren't too bad, but usually fractions are the things that feel just a little bit more tricky. So a good one to study as an additional problem. Big idea on this one, though, is things do reduce in this problem. We can divide the 2 into the 162. That's one extra thing we can do if we have fractions to make it a little bit nicer, is do the reductions where possible. So divide 2 into 162 to leave behind an 81. X power 3 divides into x power 39. At scratch work, it would look like this. 3 factors inside x power 39 cancel off and leave x to the power 36. So x to the power 36 is left behind. Then same idea with the y variable. We have y power 13 divided by y to the power of 24. Here we're using the exponent laws in the reverse way. We're taking 24 minus 13. So we get 1 over y to the power of 11 altogether. So the 81 is nice. That's just 9 times 9. We have an even exponent here. But y power of 11 is just not friendly to this problem because the index is a 2. So let's take an additional step to clean this up just a little bit further. This turns into the square root of 81. You could leave it as an 81, or you could write it in as a 9 to the power 2. That's kind of up to you and the style you'd like to write it in. X power 36. And down below, we would rather that be a y power 10 because then the index 2 would divide into it. So we put in exactly what we want, y to the power of 10. We go down by 1 power, and we can counteract that by just multiplying by y. Exponent laws will let this multiply back to y power 11, giving us the original denominator. Now, the step you could take, which sometimes is skipped over, is you could rewrite this as the square root of 9 squared x to the power 36 divided by the square root of y to the power of 10 times y. So here we use the property of radicals that you can split up a square root as numerator and denominator. Then you could rewrite it even further. If you took this additional step, you could rewrite this as square root 9 squared times the square root x power 36. We could split up the denominator as well as the square root y power 10 times the square root of just y. And if you did all those splittings across numerator, denominator to get this line, across the things multiplying to get this new numerator and this new denominator from the old values, then all you'd be doing at this stage is take square root of 9. That's just 9 itself. Excuse me, square root of 9 squared rather, or 81. Here, 2 is going to divide this power. So this is x power 36 divided by 2. That would just give us x to the power of 18. Index of 2 divides here, just leaving us behind with y power 5. And square root of y just stays where it is. But this is actually quite a lot of writing, as you've noticed. It's a good strategy to really just go from here to here. This is what's done more often in practice. Once we get a good idea of what the rules are for simplifying square roots, we can just take the root of each part independently. Take the root of 9 squared down to 9. Take the root of x power 36 to get the x power 18. I thought that was a pencil. Then likewise, take the root of y power 10 to get the y power 5. So often this is an excellent shortcut to take when simplifying these down. But this is in a nutshell is how all these problems are going to look like in this section. Just watch watch for whatever the index is. If it's blank, it's implied that's an index of 2. Make everything divisible by 2. If it's, say, an index of 5, make everything divisible by 5, and it's the same idea as before. Any questions at the moment with that last part there? Okay, next, we're going to turn to looking a little bit more into exponents and what happens when they're fractions in section 8.3. So here's how it starts out. We took a preview of this before we finished off section 8.1 at the start of class. And this is the major idea. If n is any positive integer, that means it could be thought of as an index if it's larger than 2 as a positive integer. The nth root of a just means you're dividing by n. So a to the power of 1 over n is just the literal definition of the nth root of a. So we've looked into lots of things in the calculator before when it came to this idea. For example, we've taken a look into what is the cube root of 125? Came up in a lot of different contexts, came up today more at least once. What this idea is telling us is that the cube root of 125 is just 5 to the power, 125 to the power of 1/3. And you might not have known this, but you might have actually known this and used this before. Your calculator may or may not have a cube root button like it has a square root button. So the way you do the cube root in a calculator is you take 125, raise it to the power of the fraction 1 divided by 3, and you get the 5 that we're expecting. We know the cube root of 125 is 5, and in the calculator, 125 to the power of 1/3 is 5 itself. The check would be take 5 cubed, and that gives you back the radicand of 125. So this is just kind of a new point of view, a new way to think about what is a cube root really. It's nothing but an exponent. If the root is even, we have to be a little bit careful because sometimes things are undefined like we saw in section 8.1. Let's take a quick preview of that. If we have an even index and we take the square root or an even root of something negative, these occasionally turn into not a real number. So that's the one exception that we have to watch out for. And in a calculator, say we were looking into something along the lines of maybe 16. Let's make it be, 16 to the power of 1/4. That's just the fourth root of 16, which is a 2. But if you put a negative inside here, this is the undefined, not a real number. So we'll have to watch out for these kinds of things as they come up as well. It's all because the denominator this time, or the index as a root, was even. So our major goal is just to practice with this idea. We're simplifying things down. We do have to show our step-by-step solutions for these when they come up in a quiz or exam setting, so I'll be sure to write in this emphasis on the instructions. But it's also a pretty big tour of just properties of exponents that we've been studying all along. For example, if we're going to simplify this one, the first major feature about it is that it has a negative exponent. And we know how to handle that. A negative exponent in something that's a numerator just takes the base, our base is 16, and throws it down into the denominator. Let's do that as our very first step. 16 to the power of negative 1/4 is 1 over 16 to the power of positive 1/4. So that gets us started. Now we use this idea. If we have a 1/4, that 4 there becomes the index of the root. So this turns into 1 over 4th root of 16. 2 times 2 is 4, times 2 is 8, times 2 gives us the 16. So we just get a 2 down below, computing the 4th root of 16. So 16 to the power of negative 1/4 is nothing but a 1/2. If we double check this in the calculator, here's what it would look like. 16 to the power negative 1/4. Calculator spits out a 0.5. You can click this to make it look like the fraction 1/2. Most people's calculator would give the decimal value, but that's exactly the 1/2 that we've got here. So this is the major idea of this section, just working with these now fractional exponents. The only change we're going to have from the next examples is maybe it's a negative 3/4 versus a 1/4 in these problems. Little questions at the moment? Okay, if we start this one off just like before, the thing to remember is whatever is in the denominator is the index to the root. So that means 4 in the denominator of that exponent means we're dealing with a 4th root, but it's a 4th root of a negative 16. So this one just stops dead in its tracks. This one is not a real number. In much the same way as in section 8.1, how the square root of 81, negative 81 rather, was not a real number. The index here was an even 2. The index here is an even 4. So getting this not a real number is all because an even index and the negative number on the inside. That means these are ones to watch out for. When you spot them, it's quick. Your whole thing is just not a real number for the answer, but then they become tricky problems if we miss that. Other thing we explored in the last section, 8.1, was if there's a negative, but the index is odd, this one is a real number. This one is defined, and we can say what it is. So seeing the negative here in view of what happened in part B is concerning, but that's a cube root if the denominator is 3, so we can compute this one exactly. So let's try out this one next. So major idea is that 3 there tells us we're taking a cube root. But maybe just in view of the fact that this is a negative exponent, we want this as simple as possible. Let's use this exponent law again. A base to a negative exponent throws the base into the denominator, forces that exponent to be positive. So we can just simply exchange this problem, which is more complex, for this one. The base is negative 64, so we just have to carry that part in exactly. The exponent, which was negative 1/3, is now a positive 1/3. Now we're taking the cube root of negative 64 in the denominator, so it writes in this way, equals 1 over cube root negative 64. And this one's not too bad to compute. We can check in the calculator. If we take something negative, because we have a negative in the index, say power 4, 4 raised to power 3, that gives us the negative 64. And so that's the answer to what happens in the denominator. This whole thing just turns into 1 over negative 4. Or we could rewrite it as negative 1/4 if you like. Either version would be an equivalent answer. This would just be the more typical way to write it. So these are strange looking problems, but just thinking in terms of that denominator there giving you the index to the root, we're not doing really anything too different just yet from section 8.1. It's just a different way to write the square roots, cube roots, fourth roots, and so on. See if we have another problem. Yeah, one more to try. Any questions at the moment with either one of these? Okay, this one was sketchy. It was not a real number because of the negative on the inside and an even root, the fourth root. But this one's actually okay. The whole thing that makes these two problems different is the parenthesis versus the lack of parenthesis. Doesn't even seem like a huge change. So part of what's going on in part D here is training our eyes to spot the difference. Without the parenthesis, this turns into an order of operations problem where you have to do the exponent first and then do the multiplication, which is just a multiplication by -1. But what that means for us is the thing we're taking a square root of is actually a positive randican, positive 64. So keep these two problems in mind. These are really very tricky. Part B and part D looks like they're both not a real number, but it's not the case with the negative here without the parenthesis. This one is a real number. We'll take the square root of 64, just multiply it by -1. Here, even though the traditional thing is to not put in the index, to connect the idea of what's going on, this would be a good one to write in the index directly. Just as a reminder, this is a square root coming from that denominator 2 over here. 8 times 8 is 64. So the square root of 64 is 8. And the whole thing just becomes -8. So that's a good tour of different kinds of properties we can take a look into when we're dealing with an exponent with a fraction and simplifying these integer expressions. Any last questions at all, folks, before we try out a new concept? Okay, the thing that made these problems really not that terrible is that the numerators were all ones or maybe a -1. And when they were -1s, we forced them into a +1 by properties of exponents. So that tells us what happens if we change to this new grouping of problems, where there's a different exponent m in the numerator, a different exponent n in the denominator, and m is not necessarily 1. Really, the idea is not too bad, actually. The thing you want to take away from the last examples is that the denominator is telling you what root you're taking. It's the index to the root. If you have that idea down, then the power of m just goes either on the outside or the power of m can go on the inside. Usually, this one's the better formula. It makes simplifying things a little bit easier. And this is the preferred formula if you're dealing with something involving variables. So this one is better for variables. This one is better for numerical problems, like say 81 to power -3/2. Better for numerical problems. Really, we're just directly extending on what we did on the very last problems. First thing we can do to simplify 81 to the power -3/2 feels abstract, but we'll just force the exponent positive. It gives us 1 over 81 to the power +3/2. So that's one exponent law down. Then we deal with the fact that this is just a square root, and then we raise the answer to the power 3. So that's going to be the outer exponent we're putting in. So this is now 1 over power 3 goes here from the numerator. We're taking the square root of 81, writing that in just for emphasis on where the 2 actually goes. And we're just about there. At this stage, it's just order of operations. 9 times 9 is 81. So the square root of 81 on the inside is just 1 over 9. Or just 9 rather, focusing on the denominator. Copy in the outer exponent of 3. I don't know 9 to the power 3, so we go to the calculator. 9 power 3 is 729. So the whole answer is 1 over 729. So that's the process. We just break these down into what roots you're taking, cube the result that you get thereafter. Any questions, folks, on getting through part A? Okay, let's try this out next on part B. This one looks inconvenient because if we took the same strategy, we'd be putting 1/4 into a denominator, and now it's a complex fraction. But there's other exponent laws that we can use here. Let me show you this one. Quotient, we have a quotient, 1/4 is a quotient. A quotient with a negative exponent tells you you're allowed to just flip the fraction, force the exponent positive. We used that before when we were clear back in section 5.2, but here it's a really good idea. 4 over 1 is what we would get if we flipped that fraction, but that's just 4 itself reduced. Now that we flipped it, the power is positive 5/2. That's not too bad to work with. We have another square root in this problem, so this would turn into a power 5 for the outer exponent. And we're taking the square root of 4. So again, the major way to memorize these properties is denominator becomes the root. The numerator is sort of like the thing that's on top. That's the outer exponent. All order of operations from here. So take the square root of 4, that's a 2. Raise it to the power of 5. That's 2 times 2 for 4, times 2 for 8, times 2 for 16, times 2 gives us the 32. That kind of feels like deja vu at this point. That seems to like it comes up a lot. And that's the whole value for 1/4 to the power of negative 5/2. So what's the check on this? Well, you can just put this in the calculator. 1/4 to the power of negative 5/2. And it spits out what we're expecting, a 32. That's why when these are done a quiz on exam problems, there'll be an extra emphasis, just like on the last example. You do have to show the step-by-step solution to get full credit on this, because it's more about knowing how to use the formulas, less about just jamming things into the calculator. Let's actually include that emphasis. Let's copy this down just as a reminder. Well, let's practice a few more before we move on to the next concept. Well, a couple more is what we have down here. This one has 16 in the denominator with a negative exponent, so we can rewrite this one as 16 to the power of now positive 3/4. We just convert it back up into the numerator with a positive exponent. Same rule for the numerator and denominator. This one's going to be a 4th root. So this turns into 4th root of 16. Raised to the outer exponent, power 3. Well, 4th root of 16 is not too bad. That's kind of weird. The color coding kind of broke down. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that comes out as a 2 raised to the power 3, and that one just comes out to an 8. A lot of these go pretty fast. The moment you write down this part, the root is usually pretty fast to run through. And then you're just cubing or raising to the 5th power and so on. the resulting answer after taking the root. Part D, though, is a bit of an exception. This one has us taking a fourth root of a negative 64. So an index of 4 would go right here. The radicand is a negative 64. Just like before, the outer exponent is a power 3. But now we have a bit of a major issue. We're taking an even root of a negative number. Once again, this is one of those problems that comes out as not a real number. It's not a real number, all because of the even index and the negative number here. If this was a fifth root, we could make that happen, make it work out somehow, some way, but not if it's even. Well, any questions at the moment, folks, with simplifying these rational exponents? Okay, let me take a quick screenshot just in case this is not on the next problem. We use the formula on the left over and over again on this example. I mentioned this formula is convenient if we were dealing with something in variables, and this is what the instructions would look like for that kind of problem. Here's the screenshot of the formulas just for an easy reference. Let's hide that for now. These problems go really quick, but what's tricky about example 3 is the instructions. It says change the given expression to an equivalent expression in radical notation. It doesn't mean awesome notation, it means something specific. We're putting in roots. So already that makes us kind of a confusing problem. Over here, this is the rational exponent form. Let me point to this one since this is the form that we're going to use. This format is a rational exponent. Form. But when it calls for radical notation, what they're asking us to do is write the problem in that way, involving the right root. So this is in radical notation form. So these start off in rational exponent form, and we're just converting to the radical notation form, putting in the root. It's similar to what we did on just the very last problems, except that there's now integers mixed with variables in the problem. But really, it's kind of the same idea. The denominator tells us which root we're taking, so we can start off by writing this as fifth root. But this time, to simplify the work, we're going to put the power on the inside. So this would become 2x to the power of 3. That means this simplifies a little bit further. We can use properties of exponents that says, where's the property? Two things multiplying, that's the 2 and the x in this problem, raised to a power, allows us to raise both parts, both factors, to that same power. So this is really now 2 power 3 times x cubed. Fifth root of 2 cubed times x cubed. So now it's the fifth root of 8x cubed. It doesn't simplify in this step because the exponents we see here are smaller than the index we're taking. All we're doing is just changing the notation. As an exponent to rational exponent form, you get 2x to the power 3/5. If you really want to write that in radical notation, this expression is nothing but the fifth root of 8x cubed. Well, they're really fast problems. It's really just tricky to start them off, knowing what we're doing. Really, it's just looking at these exponents again and writing them down in their rational form. Well, one thing that's really tricky about this one as well is 2 went inside the fifth root because of those parentheses, much like the problem with the negatives we saw at the start of these notes. But this one's different. There's no parentheses capturing the 8. it becomes a kind of an order of operations process where you have to deal with the exponent first, then do the multiplication by 8. So this turns into 8 times x to the power 2/3. I mean, that didn't really do anything new. I'm just emphasizing that there's a multiplication here. We have to deal with the exponent part first. This one's going to turn into a cube root due to that denominator. So this just becomes 8 times the cubed root of x to the power of 2. So the numerator power goes on the inside using this formula here. The denominator, just like on every problem we've done on this section notes, tells us which root we're taking, cube root in this case. Well, that's a pretty big tour on how these rational exponents work so far. For the next couple problems, what we'll be focusing on is just simplifying these rational exponents. Any questions at the moment with either of these examples? Okay, so next problem's really about using these properties together now to simplify things down. Oops, didn't need to put that there. Let's put this one on a clean page. So we'll just look into the exponent laws one more time. It's a great way to practice these further. Simplify each one of these expressions. We're going to assume all variables represent positive real numbers. We want to write our answers only involving positive exponents. So to start this off, this is x to the power 1/2 raised to an outer power of 8. But in this kind of configuration, the exponents would multiply. We're using this property right here, the power rule. So this becomes x to the power of 1/2 times 8. Well, let me write that fraction slightly different. 1/2, half, that's a 2, times 8. Here, 2 can divide into that 8. That just leaves behind x to the power of 4. But that's what the property was telling us over here with the exponent laws. Power of n, they multiply together. It doesn't matter if they're fractions or not. 1/2 times 8 just gives you power 4. Then the whole problem is over. So some of these go a lot faster than you might expect. Some of them are slightly annoying because you're dealing with fraction arithmetic, like this one down below. Like bases multiplied is this property over here. We add the exponents, whether they're fractions or not. That means the scratch work to this one would be you have to take 4/3 plus 1/2, add them together. The common denominator is 6. So multiply this one by 2/2. Multiply this one by 3/3. And we get 11/6. And that's really the whole bit of work on this one. The property of exponents says this is just 1 base x to the power of 4/3 plus 1/2. It's a pretty abstract looking exponent, but it's a number just like if it was a 4 plus 2. Add those together, see the scratch work down below, and we get x to the power of 11/6. And that's where the problem would end. Let me put a box on this one since I have work below just to emphasize this is the answer to the problem. Same idea on the one below. Here we're going to be using the quotient rule. But any questions at the moment? Okay, quotient rule is kind of tricky because there's really 2 different versions. Let me put the red dot where we're looking at. You can either do the numerator version, but we want positive exponents. So we want to subtract in a way to make sure that 3/4 minus 5/7 really comes out as something positive. So let's do the scratch work on that. If we took 3/4 minus 5/7, least common denominator on this one looks like it's going to be a 28. So multiply this fraction by 7/7 to get 21/28. Multiply this one by 4/4 to get negative 20/28. That comes out right. This is 21/28 minus 20/28 for a 1/28. Gives us a positive exponent. So it tells us the cleanest way to simplify this one is to take y to the power 3/4 Subtract the denominator, which is slightly smaller than 0.75, the 3/4, minus 5/7. By the work below, that's just y to the power of 1/28. So that would be the answer on this version here. We'll have a couple more that we want to practice that gets a little bit more hairy, just a little bit more steps to show. But these are the major concepts at the moment. The big thing that we want to take away is all of these exponent laws from 5.2, they're valid no matter what your exponents look like. If they're real numbers, whether they're fractions or not, the same ideas apply. Let's see if we can try one more. Example 5. We'll come back on Thursday and refresh, take a look into this last one, part E. I don't want to try to rush through that one. So let's hide it for just a moment and focus on this one here. Simplifying this expression is going to be this property. We have a product raised to an outer exponent. Our exponent n happens to be 4/5. The idea with this is the exponent n distributes to each one of the factors. So we raise each part to the power of n. So if we do that on this one, we'll get x cubed to the power of 4/5 times z power -1/5 to the power of 4/5. It's a lot to look at, but it's the same exponent laws as before. And each one of these is just a power rule. You have an inner exponent and an outer exponent. They multiply together in this kind of configuration. So this is a 3 with a numerator multiplying 4. That tells us the first thing is just x to the power of 12/5. This one, let's do it with scratch. This is -1/5 multiplying 4/5. So those are the two exponents, but that's just multiplying across the numerator and denominator to get -4/25. So z is to the power of -4/25 on this one. Now the only thing we have to make sure we check is our answer only involves positive exponents. But that's not so bad. We've been using this exponent law quite a lot in this section already. If we have a negative exponent, we just flip the position from numerator to denominator, or vice versa. If it starts in the denominator, promote it up into the numerator. This one's in the numerator, so the answer becomes x to the power 12/5 divide by z to the power of now positive 4/25. So it's a lot of stuff to look at because it's fractions, but it's the same properties as before. Instead of trying to rush through this one like we mentioned, this will be our kind of refresher warm-up problem when we come back on Thursday's class before we go into the next sections. So this will close out the notes for the day. Any last questions at all, folks, before we call it a night? Okay, so until next time, we'll be right back here on Thursday. Have a good afternoon, folks.